What specific problem does Causal Emergence 2.0, CE 2.0, aim to solve in relation to the shortcomings of its predecessor, Causal Emergence 1.0, CE 1.0?
Causal Emergence 2.0, CE 2.0, aims to address two significant shortcomings of its predecessor, Causal Emergence 1.0, CE 1.0. First, CE 1.0 relies heavily on the measure of effective information, A, which makes strong background assumptions that can lead to underestimations of causal emergence, as demonstrated in Section 3. Additionally, CE 1.0 identifies only a single causally relevant scale, neglecting the multiscale structure that many systems exhibit. In contrast, CE 2.0 introduces a causal apportioning schema that allows for the detection of multiple scales, contributing to a system's causal workings, thereby providing a more comprehensive understanding of causal emergence across different scales. This updated framework is grounded in an axiomatic notion of causation, enhancing its robustness and applicability in capturing all cases of macroscale causation.
How does the proposed method, CE 2.0, work? Please illustrate it step by step, including key components and the underlying axioms that frame the theory of causation.
Causal Emergence 2.0, CE 2.0, operates by defining a micro-macro path that identifies valid scales contributing to a system's causal workings. The first step involves establishing the causal primitives, sufficiency and necessity, which are foundational axioms that quantify causal relationships within a system. These primitives are assessed across all transitions in a discrete system, such as a Markov chain, to calculate the system-wide average sufficiency and necessity, which together inform the causal primitives, CP. Next, CE 2.0 quantifies macroscale causation by measuring the gains in CP along the defined micro-macro path, where each scale's contribution is evaluated to determine the total causal emergence. Finally, the emergent complexity is calculated based on the distribution of these causal contributions, allowing for a comprehensive understanding of how causation is spread across multiple scales, thus providing a robust framework for analyzing complex systems.
Can you provide a simple illustrative example that demonstrates how CE 2.0 operates, particularly in terms of calculating causal contributions across different scales?
A simple illustrative example of CE 2.0 can be seen in an 8-state Markov chain where the states are coarse-grained into macrostates. For instance, consider a system where states 0, 1, 2, 3 are grouped into one macrostate and states 4, 5, 6, 7 into another. As we traverse a micro-macro path, we calculate the causal primitives, CP, at each scale. Initially, the microscale might yield a CP of 0.66, indicating some uncertainty in causal relationships. Upon coarse-graining to the first macrostate, the CP increases to 1, reflecting a reduction in uncertainty and thus a gain in causal contribution of 0.34. This process continues as we assess each scale along the path, ultimately quantifying the total causal emergence, CE, as the sum of these gains, demonstrating how different scales contribute to the system's overall causal structure.
What theoretical or practical advantages does CE 2.0 provide over previous approaches for quantifying causal emergence, and how does it enhance our understanding of complex systems?
CE 2.0 offers several theoretical and practical advantages over previous approaches, particularly CE 1.0. Firstly, it is axiomatically grounded in causal primitives, which enhances its robustness against assumptions that previously limited the applicability of causal measures like effective information, A. Secondly, CE 2.0 captures all possible cases of macroscale causation, addressing the shortcomings of CE 1.0, which only identified a single causally relevant scale. Additionally, it elucidates the multiscale causal structure of systems through a causal apportioning schema, allowing for a comprehensive understanding of how different scales contribute to a system's causal workings. This multiscale perspective not only quantifies emergent complexity, but also distinguishes between simple and complex systems based on the distribution of causal contributions across scales, thereby enriching our understanding of the dynamics within complex systems.
How is the effectiveness of CE 2.0 validated or tested within the paper? Discuss the datasets or models used, as well as metrics for evaluating performance improvements over CE 1.0.
The effectiveness of CE 2.0 is validated through its application to various datasets and models, including Markov chains, cellular automata, fMRI data, and gene regulatory networks. The paper outlines a systematic approach to quantifying causal emergence by calculating causal primitives, CP, across a defined macro path, which allows for the assessment of gains in CP at each scale. Specifically, the degree of causal emergence is measured as the total gain in CP along this path, demonstrating how CE 2.0 captures all macroscale causation that CE 1.0 could not. Additionally, the paper compares the performance of CE 2.0 against CE 1.0 by showing that CE 2.0 can detect significant degrees of macroscale causation in systems where CE 1.0 fails to identify any causal emergence, as illustrated through the manipulation of an 8-state system. Metrics for evaluating performance improvements include the robustness of CP gains across different intervention distributions and the ability to elucidate multiscale causal structures, which CE 1.0 struggled with due to its reliance on effective information that made strong background assumptions.
What are the main limitations of CE 2.0 as identified by the authors, and what future work do they propose to address these limitations?
The main limitations of CE 2.0 identified by the authors include the combinatorial explosion associated with searching the set of macroscales in a system and the assumption of a particular chosen macro path to define a hierarchy of scales. This reliance on a single path may restrict the analysis, as it does not account for the full set of non-commensurate paths that could provide a more comprehensive understanding of causal contributions. To address these limitations, the authors propose developing a causal apportioning schema that integrates all possible paths while managing the combinatorial complexity. They also suggest adapting the singular value decomposition (SVD) method for CE 2.0, which could allow for capturing local and global maxima of causal contributions without the instability seen in CE 1.0. This adaptation aims to provide a more specific measure of causal emergence that can be applied to larger systems effectively.